So, welcome everyone. Thanks a lot for being here to another week's intercontinental seminar on gravity and cosmology. Today we have the pleasure to host Verónica Errasti Díez. Verónica studied physics in Madrid, and then she got her PhD in McGill from McGill at 2018. And since then she's been working in no, she has worked actually in Munich in LMU, and now she's at CUNEF University. And today she will talk us about bottomless wells of wealth. So thanks a lot, Vero, and the floor is yours.
Thank you. So I wish to start by reiterating my gratitude for the organizers to invite me to give this talk. Thanks to everyone who showed up for it as well. And let me welcome everyone, just in case I see some people coming up to unmute yourselves as we go if you have questions, and otherwise I hear at the end we will have a safe space for the shy ones without recording for further questions. There is also co-authors of mine, Jordi Gasset and Georgina Stout, in the audience, so they are welcome to unmute themselves at any point if they feel I forgot something important from our work. I'll discuss these two papers. Also, Manuel Lainz is a co-author in them. This one just got accepted for publication, so that's great. Looks like it's does not have any flaws. And we will see, hopefully we will learn why I chose the title Bottomless Wells of Wealth for my talk. But the idea is to basically have a little forum of discussion for ghost lovers. So let's see how we can make friends with ghosts. Perhaps a bit unorthodox presentation. I will begin by putting forward a bunch of definitions, just because I feel that ghost loving is a topic that is very prone to confusion and multiple meanings in which some keywords are said, and I wish to avoid, to the extent of possibility, confusion and ambiguity. So please bear with me, because right after we deploy some basic language, we can say why it is so interesting, or at least I will give you one reason why I find it very interesting. And then we will get down to the technicalities. How can we make this ghost friendship, ghost love work at the technical level? And I'll add a final twist in the plot, so let me not say anything about that and step over my own final surprise. So what do we want? So ghost is the keyword here, but in fact, I would say that it's more interesting to start by discussing the property of stability for a dynamical system. And then we will go ahead and grab that property and try to apply it to the particular case of ghost systems. So what is a stability? There are various notions that have been put forward, and it's very important to distinguish between them properly. In this talk, I'm going to be focusing on global notions for stability, and these apply to all solutions of a dynamical system. And for the purposes of later application for ghost systems, we can differentiate two flavors for it. I'll be calling them G1 and G2. So G1, in fact, is a very well-known notion dating back to Lagrange. His findings have been recently published by Cambridge University Press in a book from 2009. So you can read the big master now in a modern language, which is always a pleasure. And the idea here is that there is no solution that diverges, ever. At no point does the solution tend to infinity in any of its variables. A bit of a more relaxed notion for global stability would be G2 in my notation, and it's been called benign stability. And well, the main person here is Smilga, who put it forward already in the context of ghost systems. And what he does is he relaxes G1 to allow for solutions that diverge, but can only do so as time tends to infinity. And the rationale could be that if my instability kicks out at infinite time, well, who cares? We can even extend it further into something that one could call G3 and say, well, and what if my instability kicks at very late time, say H of the universe? Then I also don't care. I've heard Jose Beltran, for instance, defend this sort of notion, but no one has put it into play in the context of ghost systems, so I'm not going to be discussing it, but just to say that there is different flavors of global stability that one can entertain. Local stability has been far more investigated, both in the math department, people working with dynamical systems, ODEs, PDEs, and also in the context of theoretical cosmology. It applies to some solutions, not to all of them, and we can characterize the solutions that this notion of stability applies by their initial conditions. So the classic would be this L2 or Lyapunov stability. There are many different variants of it, but in essence, it says that when you have a critical point of your dynamical system, then the solutions remain fairly close to each other, basically at all times. We can entertain some loose notion or local notion of previously posed global stability. In our papers, these are called L1. Again, the person who used them and put them forward is Smilga. He referred to them as islands of stability. And this was some preliminary work before he could cook up ghost systems that would not just have islands of stability, but would have this G2 type of benign stability for all solutions. Good. So as I said, let me focus on global stability. And in fact, I'm going to take the more restrictive flavor of G1 or Lagrange stability, no divergence whatsoever. I'm going to try to formalize this notion. And for that, I am first and foremost interested in grabbing the notion of a dynamical system in as big a generality as possible. We will see later on why, but in particular, let me point out that the entire presentation is going to be intrinsic. So it's not going to be coordinate dependent because this can, in fact, play very bad jokes on us, and we wish to avoid them. So let us consider dynamical systems by their solutions, which is a bunch of curves going from some interval in time to some just Hausdorff topological space. We will require Hausdorff so that we can have a sensible notion by physical standards of topological space, and we will require the solutions to be continuous. Just paraphrasing Professor Xavi Gracia in UPC Barcelona, just to have an honest notion of a dynamical system and a solution of it, or the set of all solutions for it. Okay, so if we understand dynamical systems in this very generic manner, that perfectly well will grab the notion that you intuitively have of a dynamical system, then we can define two different flavors of already just the G1 never diverges stability notion, global stability notion. So the one that has been mostly employed in the literature would be what we call G1A, if you so please.
Sorry, Vero. Alex
Yes.
Beckman wants to ask a question.
Yeah.
Oh, hi, Vero.
Hi, Alex.
I'm just a bit puzzled. Sorry for the interruption, but I think you mentioned before that a solution is Lagrange stable if it never diverges. But you see, any runaway for any given moment of time is always finite. So I would say that so Lagrange stability actually implies that you for infinite time stay at a finite space, phase space.
Yes.
And it's not the thing, right? It's never divergence. It's a much milder requirement, which probably would go to benign stability.
So benign stability is going to allow for divergences as time tends to infinity. So you will be allowed to have things like exponential of t, for instance. And
Sure. Sure.
Okay.
But you see, Lagrange stability actually forbids you from any runaway. So that implies that you have a universal bound valid for all times up to infinity. And it's not that solution for each moment of time stays somewhere, right?
Yes, correct. Actually, all solutions will be bounded if you wish, or more stringently compact. So I'm only looking into Lagrange type of stability, and I'm going to try to say that there are two different possible ways of formalizing this notion, because after all, Lagrange did live a while ago. So we will need to reformulate his idea in a manner that we can make useful for our purposes. And we have found two ways that are not exactly equivalent, as I'm going to explain right now, to try to make that work. But you are right, a loose name, if you want, actually in the theoretical cosmology literature would be that a benign stability allows for a runaway, while Lagrange stability does not. And what we never want is a blow up, let's say a runaway in finite time. That's the always forbidden one that no one has considered. Then it's just in discussion with Jose Beltran that he pointed out, what if I have a blow up, but it happens at age of universe? How do I care? So he's the least stringent ghost lover that I have heard on this. But I'm going to go with your understanding, your and collaborators' understanding, great papers, by the way, that I want to make Lagrange stability work, just for the purposes of saying that even in the most stringent scenario and understanding of stability, one can make, or ghost can make it, as you said in your work, in your talk. So how are they going to make it? So in the bounded sense, it means that the image of the solutions for all the times in which they are defined is bounded. And this is going to call for the underlying manifold to be metric. So not just some topological space, but it should be metric. We put forward a different understanding that is more general, and we call G1 in the B flavor, if you want, in the compact sense, which says that the closure of the solutions should be compact. And now you might be asking yourself, well, is this some mathematical small thing and no one really cares about it? And I would say, no, that's not really the case. While I agree that very few people are going to go ahead and try to do some useful physics for life in P. Hausdorff, where we don't even have the sense of bounded motion because we don't have a metric to it, there do exist quite interesting topological spaces that are metric, where these two different understandings of Lagrange stability, no runaway, are not equivalent to each other. The latter implies the former, but they are not exactly the same. And they are only the same, they are only equivalent if we require that our metric space comes with a Heine-Borel property, which just basically says that any closed and bounded subset is compact. That's very intuitive, but I refer you to this excellent book to mess up with your mind. It's called, I think, something like Counterexamples in Topology. You can see quite a bit of counterintuitive and strange things happen. There are lots of examples, counterexamples, and funny things to look at. But for instance, for our purposes, we can point out that P metric without the Heine-Borel property includes Banach spaces, includes infinite dimensional Hilbert spaces, meaning that here is going to leave field theory, here is going to leave quantum mechanics, and here we are not going to have, let's say, a unique way of formalizing Lagrange stability, the loose notion that I don't have runaways. So I would go ahead and say it does matter. Good. So these are my notions of stability, and now I want to try to put them onto ghost systems. So our first notion of a ghost system is here, the ghost looking into the mirror saying, well, I'm a system whose Hamiltonian is manifestly not bounded from above or below. Please do not confuse with Faddeev-Popov ghosts. Those are not the object of interest here. And perhaps in the literature of theoretical cosmology, in a bit of a less rigorous approach, the way to look at this is maybe sometimes from the Lagrangian point of view, and then we see that we have a negative kinetic energy mode, and that's called the Ostrogradski ghost. That is the way in which I would like us to discuss ghosts. It's typically differentiated from having unboundedness from below, from Laplacian instabilities, which comes from the Laplacian piece, or tachyons, which comes from the mass term. But as it turns out, it's kind of tricky to make this division, because Wolf and Lagos explicitly put forward a set of canonical transformations that, for some concrete examples, take you from an Ostrogradski ghost into a Laplacian instabilities into a tachyon. Therefore, you can, let's say, unbound from below your Hamiltonian in different ways, and it remains unclear if there is really an, let's say, geometric intrinsic way of differentiating this type of unboundedness pathologies from each other. So let's go by the general first understanding that we just have a Hamiltonian that has no bound from below, no ground state. And that will be our ghost system. And why should we care? So Alex, thank you very much. You simplified my job so much, because in March you gave this same seminar. So I presume that everyone here has heard a very detailed list of extremely diverse and compelling reasons why ghost-ridden systems are fantastically interesting. And let me just therefore point one out that I like and that I find befitting for this audience interested in gravity and cosmology. So it turns out that we cannot yet explain the entire universe, no surprise here. And in our attempts to try to account for the missing pieces, we keep constructing new theories. We generalize general relativity. There are many proposals. An umbrella term is modified gravity. There exist many different reviews for it. I particularly like this one, but the field moves so fast that it's never bad to look into the new reviews that keep coming. There are other examples where we again are trying to generalize very well-known theories beyond the standard model. Electrodynamics is currently very fashionable. There is MOVMAX that came into the show in 2020, and it's been explored with enthusiasm. The Lux experiment that I always like to mention, that is going to happen in DESI, is going to provide the first ever direct detection of the non-perturbative regime of QED, and it's starting to gather an increasing number of theoreticians to put forward compelling models and do the typical battle, okay, until you provide the measurement and you declare a winner and a bunch of losers, more than a winner. Let's see what we can come up with. And there are also higher order extensions, and the most well-known one remains Podolsky's proposal from over 80 years ago. So let's look into the case of modified gravity, which should be of interest to this audience. And let me say that I'm particularly interested in adding higher order terms to general relativity, that type of extension. And what happens when you do that? There is some non-trivial massaging that you can do to bring your theory to a first order form, where you can start to detect these Ostrogradski, Laplacian, tachyonic type of instabilities, break down the bottomless of your Lagrangian, Hamiltonian. Good. And what happens is that you start developing ghosts, kind of fast, kind of hard. The picture is a bit outdated. Sorry, Tessa Baker, for disgracing your lovely graphical summary with some ghosts. But my point is that actually what remains in this realm is basically constructed out of the premise, kill the ghost. Just kill, exorcise, ghost bust. I mean, all good jokes are taken, so I have no hopes of originality in this front. Just can you cook up GR plus higher order terms in such a way that there is no ghost appearing? For instance, toast would be a fantastic exemplar of this sort of game. Now, this construction pattern is quite restrictive. So typically, if you add higher order terms, you're going to add up in a ghostful scenario. So why is it that one requires ghost freedom? There is a false implication that is deeply rooted in the literature that having a ghost necessarily implies an instability. And that's just not the case. A very good defense of the falsehood of this implication has been done by several authors in different styles, different levels of technicality. I recommend all of them. They are very clear in their arguments. For me, it's rather easy to say this cannot be true because, in fact, we don't have just one, but we have an increasing number of counterexamples for this implication. We have it in the G2 flavor, we have it in the G1 flavor. It's worth pointing out there is this very strong school in Tomsk that I feel is undercited. They are doing a fantastic job at ensuring bounded motion. And also we have Vigman, Alex, hello here. Great job with Held. I think I also saw him, Defayette and Mukojama. They put forward a very broad class of theories that are also G1 Lagrange stable, no runaway, fairly recently and exquisitely proved that they are globally stable, no runaway. Now, why should we care about that space that opens up for adding higher order terms to say GR and allowing for a ghost while still requiring that the setup is stable? I think a very interesting idea was given to me by Professor Yanagida when my co-author Jordi Gasset and I visited in Tokyo last year. And he said, well, look, so ghosts do tend to give rise to instabilities, but they not always do so. So there is some sort of fine-tuning happening here. But if we are discussing, say, the universe, and it's been going on for almost 14 billion years, you definitely want some notion of not blowing up anytime soon. And if a ghost-ridden system has to satisfy special requirements for being of this form, that could be a legitimate fine-tuning. That could explain, for instance, perhaps why the cosmological constant is so small if a bigger value would land us in an unstable scenario. So the idea has not been materialized, but I think it's extremely appealing and worth giving a second thought. I thank Professor Yanagida for his intelligent conversations. And I will declare ghosts more than motivated, also thanks to Alex's talk 2 months ago or 3 months ago, I think in March. Let's move on to the technicalities. How do we make this work? So first of all, how does it work in a normal scenario where there is no ghost? So, okay, we have some sort of dynamical system, and let's suppose that we have a Hamiltonian that is not time-dependent explicitly. So therefore, the energy is a conserved quantity of the system, and let us say it is very, very nice. It is twice differentiable, has a global minimum, its Hessian is positive, definite everywhere. Then the system is G1 stable. So Lagrange is stable. And because P is metric with the Heine-Borel property in this case, it doesn't matter which of the two flavors, bounded or compact, we use for this definition. It will always be G1. So here is just for the sake of completeness, a conserved quantity is exactly what you expect it to be, some continuous function that keeps the same value throughout the solutions of the system. And why does this work? Well, here is a visual, sorry. This should not be x dot, this should be p if I am in phase space plotting the Hamiltonian or energy. So let's look at the harmonic oscillator, right? And then if I take a section here, you see a sort of ellipse, right? If I take a section, that's my constant energy, and that's what I call a level set, that ellipse in particular, and solutions must live within. And because this one is a bounded slash compact object, my solutions, all of them for the system, will be bounded slash compact for any slicing that I decide to do. Very good. Just a notational approach. We will be calling the level sets with this negation sign here. Perhaps it's a bit unconventional, but we find it's very unambiguous. So stay tuned for it. It will show up again. So this is the regular case, but a ghost system does not have a minimum by definition of what we are considering a ghost system. So how do you make this idea work then? And lo and behold, what you do is that you replace the energy by another conserved quantity that will have all these very nice features. And this is, in fact, the magic, if you wish, behind the Pi-Uhlenbeck oscillator. It has a different conserved quantity that is not the energy, but that satisfies everything that you typically put on the energy to make your ghost work in the no runaway sense. The Tomsk school is also heavily based on this trick, if you want. In fact, it's not just a trick. They have very serious work going on. Yes,
Sorry.
Alex.
Just a very small comment. This Pi-Uhlenbeck is a linear system, so therefore there is no problem, right?
You are breaking my final twist of the story, Alex. Please, I will come to it. Just because I'm pointing it out, because all these sort of studies, they did begin with the Pi-Uhlenbeck, and it's the model that has gathered most of the attention. And I didn't want to ignore so much good work done. But indeed, later on, it was realized that, in fact, Pi-Uhlenbeck never had a ghost to begin with. And I'll make this statement precise. So in a sense, it's not a valid example, but I would call the Kaparulin et al. Examples very legitimate ones. They do cook almost systematically. They have a procedure to generate systems that will have a Hamiltonian that is not bounded from below, so ghostful, and how to cook up systems which come with a different conserved quantity that will have inbuilt all the properties that you typically want from the Hamiltonian, so that the ghost in there is stable. A more general approach, and please jump in, Held and Wigman, because if I say it wrong, this is your work for sure. One can be less stringent. You don't need so beautiful a conserved quantity as you typically demand with a positive definite Hessian. Instead, you can work on the idea of coerciveness. So visually, basically, the difference is my conserved quantity that is going to do the joke, basically looking like a harmonic oscillator, and this is indeed the harmonic oscillator perfectly, or is it a bit something more relaxed that ultimately anyways does the job, as I can always see, cut the level sets here and see that they are bounded slash compact, and therefore all my solutions are going to not have a runaway. I think it's a very intelligent trick to make this relaxation. And in our work, how did we take that further? So we basically invented a new property for your conserved quantity so that it need not be as beautiful as the energy typically is. It need not be coercive, which is less beautiful, still beautiful. We invented the notion of a confining function, which basically means that the path-connected components of the closure of its level sets are compact in P. Hausdorff. So this property that we are requiring is completely original. It's put forward just for this case to try to generalize it as much as possible. It has a higher realm, broader scope of applicability, and is less demanding. So in particular, you can see that being confining implies, and we actually proved it in our work, implies being coercive, implies being positive, or it can contain. And you can cook nested examples, like the one I show you here. I put the formula so that we can have a concrete idea of what it is that we are talking about. But this would be a particular example where A and B and alpha are my free parameters. So sorry, B and alpha and omega are my free parameters. And if I take B to be exactly equal to this combination, I will end up in the topmost scenario where I have, this goes on and on forever. I have infinitely many global minima. This is not coercive. It does not ultimately all stretch out into infinity, keeps coming down every time. And if I exceed this bound, then I land in the bottomless scenario where I can have infinitely many minima, and none of them are bounded. And these are plots not of the potential side of the Lagrangian. Please be careful. These are plots that of this F, just so that this F, you should know, enters also the conserved quantity, that is not the energy, on which we are placing the burden to analytically prove global stability, no runaway, for a ghostful system like this one, where you can clearly see the negative kinetic energy term in the usual theoretical cosmological understanding of a ghost system. It's right there on your face. Very good. So hopefully you can see that this allows for greater generality, and there is a twist in the plot that Alex was already warning us about. So look, you do a lot of good work already to arrive to this sort of results or previous results, because you need to come up with a system that has basically a ghost in your face, so a Hamiltonian that is really not bounded from below. And you need to somehow very carefully select your system, because it will need to have another conserved quantity, and these are never easy to find. So different proposals have been put forward in the literature, quite smart ones, on how to cook up systems that will come with another conserved quantity, and then you kind of wish very hard for that conserved quantity to have the most beautiful, less beautiful, or enough properties to be able to really make that ghost not run away from you. And after you have done so much work, and it really is quite a lot of work, it turns out that stable ghosts are professional ghosters. So Smilga in 2008 pointed out, referring to the Pi-Zullenbeck oscillator precisely, that it is misleading to say that the ghost problem was resolved therein, since there is no serious problem to solve anyway. You can bring your Pi-Zullenbeck oscillator to the shape of two decoupled harmonic oscillators, where one is, if you want, twisted down, but this is just a direct sum between Hilbert spaces and vector spaces, and then you can, no one cares about an overall factor sign in front of one of them. The same idea can be extended to say, well, what if the following situation occurs to you? You have a ghost system, so your Hamiltonian is not bounded from below. You manage to cook something that has a nice enough conserved quantity, additional auxiliary conserved quantity, that helps you prove analytically that there is no runaway. But now that other conserved quantity is itself a Hamiltonian of the system, and it's not connected canonically to your original ghost Hamiltonian. So we are talking about something stronger, more particular than integrable systems at the moment. We are talking bi-Hamiltonian systems. So I would say that it would be fair to point our finger at such proposals and say that they can be very nice proposals, very interesting proposals, extremely good work done, but that's not a stable ghost. If you have two equivalent Hamiltonian descriptions and you are a ghost in one of them, but you are not a ghost in the other, then, as Kaparulin et al. Argue, what you should be doing is you should be quantizing with respect to your non-ghost Hamiltonian. And I would just call that a false ghost altogether. These are fake ghost lovers. That does not solve a problem because the problem was not there to begin with. If you want to call something a ghost system, then even if it is bi-Hamiltonian, in the event that it happens to be bi-Hamiltonian and admit several inequivalent Hamiltonians, then all of them should be not bounded from below. And you might think, again, this is some sort of mathematical fancy and not very interesting, but that's just not the case, because when you sweat a lot to have a ghost system and to be able to stabilize it with a conserved quantity doing the job that the Hamiltonian by definition cannot do for you, you do end up quite often into a bi-Hamiltonian system at the time being. So there is a need to complete the argument. If you are calling for a conserved quantity that does the job, you should ensure that that is not in itself a Hamiltonian of the system in the case that you are working with either positive definite Hessian or coercive notions for your conserved quantity. You can only be safe if your conserved quantity is of this type, because then even if you check and you happen to be bi-Hamiltonian, as we are here, then you still can claim that you are a ghost-ridden system. So careful with that. Do not finish your work without making sure that you do not have an existential crisis and you're supposed to be ghost is not there. Yes, Alex.
Of course, I could not miss this opportunity to ask you. So usually there is a simple, I think it's called Darboux theorem, right? That this symplectic form can be put into canonical one. And in that case, it's completely fine to say that you have well-defined canonical description of a ghost system, right? If you do it with non-canonical symplectic forms, sure, I can write many different Hamiltonians, but why don't we do it in other physics? I mean, there is always a canonical description. The question is, like, you can write, of course, two different Hamiltonians, but they would correspond to two different symplectic structures. Am I right?
So the notion of a bi-Hamiltonian system is quite subtle. So the point would be that you do have two different Hamiltonians, each of which has their own canonical symplectic form. What happens is that you cannot go through a canonical transformation from one description into the other, but they are both legitimate descriptions of your system. So there is no way in which, if you want, the second Hamiltonian is weirder than the first. And that is the case of the Pi-Zulenbeck.
What we choose as your time translation generator. Solutions are not the same, right? If I write,
yes.
So it's two
solutions
different
are the same. These are two different equivalent ways of describing the same system. So you might even have been looking into a system that you just were not aware was of bi-Hamiltonian type. So you just grabbed one of its Hamiltonian descriptions, you solved it, etc. And let's say that another different person, not knowing anything, goes ahead and looks at a supposedly different Hamiltonian, cooks the equations of motion, solves them fully, incredible job. You will be discussing the same system. It's the same dynamical
wait a second.
system.
So if I take, sorry for the interruption, maybe we postpone it, but it's a very simple question. I think it's central to what you're discussing. So if I take, let's say, our example with, let's say, Shinji and Cedric, and there was a conserved quantity. So if I use this conserved quantity as my Hamiltonian, I don't think my solutions for equations of motion are the same. If I measure Q and P at each moment of time, they will be different. Are they, or am I missing something?
May I?
Yes.
Because I tried to make this computation with your example, and there are two possible situations. One of that is that the same symplectic form with this new concept quantity works. So you have the same structure of positions and momenta, and it happens that another time translation gives you the same dynamics. But it also could happen that you have to change your symplectic structure. So what it means, what is a position and what is a momenta. And this is harder to actually check because you have a lot, the pair of concept quantity and the symplectic structure, you have to change both. So it can be quite involved to be exhaustive.
But let's say in the example which we had, or in set with examples which we have with Aaron, Shenzhen, Cedric, is it true that I can just really take my Hamiltonian, I calculate dynamics, P and Q at each moment of time? These are physical quantities, I can measure them. And then I can run dynamics using the integral of motion, and I will get the same answers.
The point is the relation between a concept quantity and the associated dynamics depend on the symplectic form. So
sure, but you claim it's all canonical. If it is canonical, can I really solve in the same way? Surely, if I suppose that the second Hamiltonian, if I take Hamiltonian to be my integral of motion, surely the Hamiltonian will be my integral of motion, what was before the Hamiltonian, but I will have different dynamics. Is it correct?
No, but the dynamics associated to a function depends on the symplectic form. So if you use the same symplectic form, in your case, you have different dynamics, so there's no problem. But the question is, okay, if I choose another symplectic structure,
no, but then it's not canonical.
Then the dynamics will, for the same function, the dynamics will change. So,
but it's not canonical in that case, right?
There is no sense of canonical in this sense. What you have is you give the symplectic form, and then the Darboux coordinates give you the canonical position and momenta. But if you start with a different symplectic form, then you have a different pair position and momenta, and a different way to relate from a concept quantity and dynamics.
So wait, so but still I'm not sure. So at the end, if I measure P and Q and the examples which we cooked up, it's not the same that there's the same dynamics of P and Q if I take the integral of motion as the Hamiltonian instead. Am I right?
Depending on the symplectic form you use, you will obtain different dynamics for the same Q. So the question is, there is a symplectic form that gives you the original dynamics. It could be the case or it could not. And that's not easy to check in general. There's all
but for our example, is it the case or it's not?
I don't know. I just checked the case. If I use the same symplectic form, Q gives different dynamics. That's true.
Different dynamics. Good.
Yeah, but I have not checked all the symplectic forms. That's not easy task to do.
No, of course. That's not easy task. But I mean, formally speaking, what I care about is canonical forms. And then if I take one canonical form, then I would need to do a lot of transformations to see that there is another canonical form. I don't know even how to think. But sorry, let's postpone it because I don't want to interrupt you too much. Sorry about that.
Okay, thank you both. So for me, the point would be that before we discuss canonical coordinates, the first thing you need to do is define your Hamiltonian system. And that requires not only the Hamiltonian, but also the symplectic structure. It comes as a pair. So it's kind of unfair to demand that your system, dynamical system, is fully defined by just the Hamiltonian. You need the symplectic form as well. And then you can see that there are different pairs that describe the same dynamical system. And it's not easy to relate the pairs between themselves. So really the bi-Hamiltonian check is not easy at all. There is an existential crisis. And and resolving it is not quite so simple, depending on the system. We did check ours, and it was falling into a particular simple scenario where it was fairly straightforward check. We, in our examples, in the concrete examples we give for how to solve your ghost problem a la complete unboundedness from above and below of your auxiliary conserved quantity. And therefore it is a ghost system, even with the remark of are you or are you not a ghost? I would like to finish before the conclusions with a wish. I think you might be sitting there in your home or workplace and thinking that this service was awful. How can you use this new idea of a confining function? How is it good for you? How can you actually make explicit use of it? And I would say I agree. I personally am a terrible waiter, and I apologize about that, but I would like to call for collaboration. I need to better understand what are the objects that can be modeled with a stable ghost. So I know that Jim Klein has worked quite hard. He's also from McGill with ghost proposals for dark matter. I think it is structurally possible to try to account for dark energy in a ghostful manner, but I need to understand what is my object of interest, and even more importantly, I want to understand, given an object of interest where these models could be applied, what is exactly the stability notion that you would like it to have. Do you want a global or local stability? If you want a global stability, do you want it to be with no runaways, with only runaways? Are you happy with blow-ups as long as they happen arbitrarily long in time? Let me know what are your wishes. It would be a lot of fun to work together. Let me conclude by restating that we should really move forward from the lore that has the implication that ghosts are necessarily unstable. That's just not the case. There are many counterexamples. The most stringent notion of stability, global no runaways that you can think of. So for all solutions, no runaway at all can be made to work. There are at least 3 manners calling for a conserved quantity that does the job: a la energy, coercive, and confining. The question is there something beyond confining? Is confining really tight? Is the last step in this logic, or is there space beyond? That's a really hard question, but I think it's a very interesting question. Now, be careful, because by the time you consider you may have succeeded in stabilizing a ghost, your system might turn out not to be a ghost in, let's say, the most stringent purist understanding possible, that if you have a bi-Hamiltonian system, that conserved quantity that was making the wonder for you while being bounded from below happens to be the Hamiltonian in the pair Hamiltonian symplectic structure that provides an equivalent description of your supposed ghost system. I would actually not call that a ghost, careful. That's really, really hard. It tailors perfectly well with extremely difficult mathematical questions, such as exhaustiveness of conserved quantities for a given system, such as bi-Hamiltonian structures and checking their compatibility or not. And Alex already did a great job, so let me just remind you that you should be suspicious with numerics, because these ghost systems also like to blow up at a kind of long time. So you might be running your numerics, and for that you already chose some initial conditions, so you will never be able to span all of them. You will never have a numerics proof. And B, even if you want to do it as a safe check, and we did safe check ourselves on a bunch of times, but you can actually never know if in the next iteration you will start having a blow up. And last but not least, can we go beyond the paradigm of ghost stability in terms of analytical proofs that we have right now? You must have seen that we are completely tailored and dependent on finding conserved quantities on which we will put the burden of ensuring stability. It would be so great, and I have no idea how to do it, but to stabilize a ghost without calling for additional conserved quantities. So overall, I think there is kind of a lot of possibilities, and most of them probably are not yet explored on how to make work. Ultimately, these are toy models for ghostful higher order theories. And I think theoretical cosmology is a field that would benefit from being able to apply and make these kind of systems work. And without further ado, I will make one last bad ghost joke, and thank you for your attention and take on more questions.
Thank you very much, Vero, for the really nice talk. Are there any questions from the audience? Anyone?
Well, if
Yeah,
nobody
go ahead,
is
Alex.
asking, I can ask.
Yeah, go ahead.
Look, that's actually a very, very interesting issue, what you raised. That basically, you can think about these dynamics. Maybe there is a second Hamiltonian for that. But the question is, like, how should I see it, basically? How should I measure it? So, for example, in our examples, which we had with Shinji Cedric and Aaron, we know what dynamics is. That even each moment of time, if I provide initial data, I know what Q and P are later, and I know what Hamiltonian I used. So if I take another Hamiltonian, that's in a different system, right? It's clearly physically distinct because by measuring, starting from same initial data, measuring Q and P later, I will get different results. Am I right?
No, by Hamiltonian systems are by definition systems that admit two different Hamiltonian descriptions. So you are really talking
Same
about
canonic form or not?
they are
Because of
not canonically connected to one another. So it's not just a change of variables that is going to take you under them.
Sure.
You really, I can pass you some references that is basically what we tried doing. We tried to check if we fulfill any of the sets of conditions that mathematicians who are experts on bialgebras have put forward to try to check when something that you would naturally be calling just your conserved quantity is in fact promoted to, let's say, a second Hamiltonian. So KDV system is an example of bihamiltonian. Pi-Zullenbeck is an example of bihamiltonian. Deformations of those systems have been proven to be bihamiltonian. In general, it's not simple. I'm not an expert on bialgebras, but there are lists of sufficient conditions that are algebraic, so that what you can do is that if you suspect that you are looking at a conserved quantity that might in fact be a Hamiltonian and a different Hamiltonian for the same system, you can try to check if those sufficient conditions are fulfilled. But I'm not even aware of an exhaustive set of conditions that you should check that are, let's say, sufficient and necessary. But maybe Jordi knows better than I do. I'm really not an expert in bialgebras. I just happened to meet full force by Hamiltonians in this work, and I cannot say it was a pleasure.
I think Shay wants to ask because I may postpone my question for later.
Thank you very much. It is so I'm not an expert in this field. I'm just curious, like, so in terms of like this looking for conserved quantities from systems that we know that already contains ghosts. I'm curious about whether there are some systematic way of looking for these conserved quantities, or at the moment we can only like, check case by case.
So that's a great question. It's very difficult. I would say there are different, very clever proposals in the literature, in the ghost literature. So as a mathematical question, give me a dynamical system. Now, given a dynamical system, please tell me the exhaustive set of all the conserved quantities in the system. That's an open question. It's extremely hard. Now, for the ghost systems, people have been extremely smart. So, for example, there is an almost systematic method by the Tomsk gang, Lajahovic, Kaparolina, Bakumova, and they are able to, starting with a good enough system, how to deform it so that you can preserve. In particular, they start with systems which have already two a priori known conserved quantities, and how to make deformations of those systems to create new systems that maintain a deformed version of those conserved quantities. It's really extremely good and clever work. So this is one way. Another way, which I find extremely clever as well, was put forward by Smilga, and I think it's very clearly reviewed in his paper with Robert. And that would be, he cooks G2, not G1. So he allows for runaway, but just not blow up. So it's global notion of stability, but he's perfectly fine with going to infinity at infinite time. And the way he cooks these systems is he starts from a seed Hamiltonian. It looks extremely naive and perfectly well done. And he has also generalized to multiple particles and also put forward field theory, a little bit too fast for my taste, but okay. So he takes a starting Hamiltonian, and then he gives you a prescription of basically three changes that you do into it, so that you end up with a larger Hamiltonian that has the original Hamiltonian as a conserved quantity. So the original Hamiltonian is no longer even suspectful of being a bi-Hamiltonian description of the same system. It's just, it is promoted into a conserved quantity of the bigger Hamiltonian cooked from it. So that's another systematic. And I would say the last very clever trick that was put forward was by Alex, Saron, Defayette, etc. So they take already integrable systems. So they work with two particles in mechanics. And then, so they say, okay, let me look at integrable systems. And then I do a complexification of the variables. And as long as my end result remains real, again, I will automatically have a integrable system that I can work with, and I can try to see if it is stable or not. And I think this is the very clever way in which they were able to start with a very good guess and then be able to demonstrate stability for it. So you can come up with different ideas. Overall, what we did in our work was, for instance, good brute force calculation, where you take a Lagrangian, you leave as general as possible a potential, you start putting forward ansatz as general as possible of a conserved quantity, and you go fine-tuning everything until you find a system. It's painful.
I see. Thank you very much.
Good. Any other questions?
May I still return to this bi-Hamiltonian? Oh, maybe Aaron wants to ask. Why?
Yeah, let's circle around. Yeah.
Yeah, I'm also still confused about the bi-Hamiltonian and what you actually mean, but I have a different question first, and that concerns your last point about moving away from conserved quantities. Because I agree, I think that's sort of because irrespective of whether you have this bi-Hamiltonian at the back of your mind or not, conserved quantities it's somehow a special structure, right? And we expect that at least generic corrections would violate that structure. So do you have any thoughts on how to move away from conserved quantities?
Not really. I mean, the blatant case is, of course, give me a dynamical system and be able to analytically solve it. Then you can take those solutions and see if they blow up or not.
No, but this,
of course,
basically by definition, you can't, right? Because you don't have the conserved quantity to solve it. And so I'm getting to this because I think your numerics are unreliable is a little bit too harsh. So I think that while it's true that numerics cannot provide like an analytic proof, I think our only chance is sort of the relation between systems where we have analytic proofs and then some understanding about when we lose that analyticity. So I would say that numerics on their own are no guaranteed proof, but I think the key is to sort of understand the criteria that we can understand in analytic systems and sort of lift them to systems where we don't have conserved quantities?
So I would say yes. I only want to say numerics are unreliable in the sense insufficient for analytic proof, which is what I do for a living. So I agree with you, perhaps not the best wording. I take it back and I can point out the work of Turner, Taira, Fring. They are also doing amazing work at some deformations of the KDV system. And they go back and forth from numerics to analytic results. So I do think that I have to agree. There is evidence that it can be an incredible intuition builder and point you to the right corner in the right direction, even though it does not give you an analytic proof, which is what I meant to say here. Now, how to go beyond, because KDV is again bi-Hamiltonian. So how to go beyond conserved quantities? For me, it's a paradigm changing question. I'm very sorry, I have no idea. I'm dying to know. I actually don't even need to be, it doesn't need to be me who does it. I'm genuinely fascinated by anyone who manages to do it. And I'll read it in complete euphoria. I don't think anyone has even come close to putting forward an idea of a way to go forth in that direction.
And just to be clear here, you really mean a global stability proof?
Mm-hmm. Correct.
Because I think
Lyapunov stability has been worked out in many examples. So this would be for global stability. I would even be willing to relax it to G2. So run away at when time goes to infinity. For me, for the mathematical purposes of overcoming such a difficult jump in the logic, for me, any global notion of stability is good enough. Although my personal wish is for a better understanding of what stability is tied to a given physical observable that is seeking for an answer.
Okay, final comment would be that this is sort of this is a really high standard, and in some sense we are working with physical systems all the time without ghosts, in which such proofs don't exist either. So I think it would be super nice to have such a result. I agree, but it's a standard which is higher than on other systems that we are perfectly happy working with. Good, thanks.
But absolutely.
High standards are good.
I also feel that just somehow talking about a ghostful system hopefully is being demystified, because there remains many audiences where you just can't even talk about the idea. It's somehow extremely confronted, and I think that has contributed to lifting the level of requirement for papers working on this topic to a point where it's not commensurable with non-ghost systems. I absolutely agree with you. I don't think perhaps is so much needed. If it has a good phenomenological match, then it will motivate further studies, and it will also legitimate bigger detail. And otherwise, it's just taking a bunch of examples and trying to push the theory as much as possible, just as a matter of trying to prove that there is some space that is not being explored. And the reason why it is not being explored is not a good reason. It's not properly argumented.
I completely agree.
There's another question in the chat. Sorry, Alex.
Sure.
When you say a conserved quantity can be served as a second Hamiltonian, do you mean the conserved quantity forms a level set on phase space with certain symplectic structure that generalize the cycle?
Okay, so hi Amoeba, thank you for your question. Glad you like the talk. Let me reread it. So in fact, if I am calling H my naive Hamiltonian, right, and Q is the conserved quantity in the system that I'm trying to fine tune so that it will make everything work or something, I would say that that Q gets promoted to, let's say, H tilde, and it will have its own symplectic structure omega tilde. And that's what I mean when I say careful that if you are looking at Q and understanding as a conserved quantity, just make sure that the machinery that there is in the mathematics literature does not imply that that Q is in fact an H tilde altogether. So a conserved quantity of Hamiltonian type that generates its own symplectic structure omega tilde, on the basis of which you can provide a different description of the same system. Does that answer your question? Wonderful.
Anyone else, Alex?
By the way, I may still continue because I still don't understand this story. So let's take Hamiltonian system. Let's say the one we were, like one of the many we cooked up with Aaron, Shinji, and Cedric. We take one, and then we have P and Q. Now I do arbitrary transformation of P and Q, right? I introduce new P, new Q. Then if this new P and Q do satisfy canonical Poisson brackets, it's a canonical transformation, correct? And if it is a canonical transformation doesn't change the value of the Hamiltonian. It changes the form, but doesn't change the value. So therefore, what used to be unbounded from below stays unbounded from below. So therefore, if you claim that there is a bi-Hamiltonian, you need some non-canonical, let's say, form omega, which is not the standard symplectic form, not canonical one. So that's probably possible, but that would actually, let's say, for quantization, imply non-canonical Poisson brackets, non-canonical quantization. Am I right?
No, that's not quite the case, because the thing is that that is the I would say this is at least how I have come to terms with it. I redirect you to the work by Abakumova, Kaparuli, and Lajakovic. I think they explain it quite clearly, and you can see
I know
concrete
but you
examples.
see, to be honest, I never truly understood what they're writing, so therefore I'm trying to understand what you understand out of the story. Because it is a definitely true statement that if I do canonical transformation, basically, if I do arbitrary transformation on my phase space, P and Q are mapped to new P prime, Q prime. If Poisson brackets are conserved, there's the same symmetric brackets. I mean, same delta IK, right? In that case, it is a canonical transformation, and canonical transformations don't change the value of the Hamiltonian. Now, probably they're non-canonical transformations, but then I don't understand what does it mean by this non-canonical transformation, because then I don't preserve the Poisson brackets.
No, you don't. You have a different, so you have a single system admits two descriptions. They are not related by a canonical transformation.
Perfect.
Each of the descriptions comes with a Hamiltonian with its own symplectic structure that generates its Poisson brackets. You can find Darboux theorems for canonical coordinates for each of them, and you cannot relate those coordinate descriptions to one another in a canonical transformation manner.
Perfect,
So
perfect. But that would imply that actually now my Poisson brackets are equal to this delta. Sorry, to omega. What is it called? Omega ij, right? And now the point would be, okay, I have non-canonical systems. That's fine. Maybe you don't want to go to canonized Darboux form if you want. But then actually it's much harder to, I think, quantize the system, because you have now Poisson brackets which are not quadratic, right? You have something on the right-hand side, and then it depends, because then after that, the equations of ordering all the things will pop out.
No, you will have two different Hamiltonians with their symplectic form, with their generated Poisson bracket, and they can have their own Darboux theorem, and they will therefore be canonical, and you will just not be able to relate them through a canonical transformation.
Wait,
So it's
then
a
I
more
don't
complicated
understand.
structure underlying that is
Wait,
called a
wait.
bialgebra.
Yeah, but I'm a simple-minded guy. I take P and Q. Now I write P prime, Q prime, two functions on, okay, not two, let's say 4 functions, on my previous 4-dimensional phase space. Now I check with respect to new Poisson brackets. If you say it's canonical transformation per definition. Am I missing something?
I don't know, Jordi, do you want to take over?
And maybe to emphasize in more detail one of your points, is that you have two structures with its own canonical coordinates. So if you try to write the bracket of one with the coordinates of the other, you will have non-canonical things. But if you use the canonical coordinates, the Poisson brackets will look the same in this sense.
No, but look, the thing which preserves Poisson brackets is canonical transformation, period, no?
But they are not the same bracket.
What does it mean not the same? It's same canonical bracket. dp, dq,
No. I think what you mean for canonical, because for my understanding, you have to specify symplectic form. And with the symplectic form, you define canonical in relation to the symplectic form.
Sure. But look,
So if you change symplectic, there is not a priori canonical before setting your symplectic form.
Sure. But I'm a simple-minded guy. I define you what Poisson bracket is. It's d over dq, d over dp, minus, you do commutator out of this. So that's defined. Now, if I do a transformation in P and Q, right? Now I say that I have P prime, Q prime. And there, of course, the Poisson bracket is again defined in P prime, Q prime. So if I can do that by matching it, by transforming it after that, right? If this transformation preserves the Poisson bracket, I'm done. Am I right?
But we are in the case when this doesn't happen.
But you see, that's exactly what I don't understand, because you claim that Poisson brackets are the same canonical brackets.
No. I mean, if you write them in coordinates, in the canonical coordinate in each one, they look the same, but they are in a coordinate-free way, they are two different tensors.
And they also have to satisfy certain compatibility conditions. It's really not easy to have this bialgebra structure. So you have to have a bunch of non-trivial relations be satisfied so that you can have the full mathematical construction that allows you to have two very distinct descriptions of the same system. And you cannot try to shortcut from a coordinate-dependent description. So you need to grab them from the symplectic forms, make sure that the symplectic forms are related.
Sure. But there is a transformation, it's diffeomorphism, right? I take Q and P and I map it to new, whatever quantities you want to call them. Am I right or not? Time-independent normal diffeomorphism in this phase space. But in that case, isn't it not a canonical transformation if new variables have again Poisson brackets? So that's, you see, what am I missing something? Because look, I take whatever book on, let's say this one, right? The standard one. I know what to do. So now, am I right? I just transform it and get something new? Like there's something more there, no? There's some big assumptions there. Either it's not a diffeomorphism or there is something else, no?
Alex, I think you're just confusing the things like, you need to do not have your Lagrangian system, you just have your Hamiltonian system, and then you change the variable. So the claim is that in the new system, your Q and P's are different. Like your coordinates and your momenta are not the same as you have called them before. So basically your Lagrangian submanifold is different. So basically it's just another description. Of course you cannot quantize it the same way probably, but I don't care about nonsensical things like quantum physics. But somehow you can just, you just go to other variables. So you have another structure, another symplectic structure. So it just,
No, wait. Symplectic structure is in canonical form, no?
What you call coordinates and what you call momenta. So that's the difference.
No, look, this is exactly canonical transformation. If I can rename them in whatever way, right?
No. It's not a canonical transformation because you have the different.
Sure. That's exactly what I want to understand. It's not a canonical transformation. Very good. So I can create whatever transformation. In that case, I will get whatever new omega there, right? Or it's not a transformation. It's an active map. What it is. Because you see, if I do, let's say, active transformations versus non-active, if I just do transformation of my P and Q, it's my passive transformation, if you want. Then, of course, I can only be canonical. Now, if I do a map, right, I map this phase space into something else. Then, of course, I could have different things. But, you know, then I can map whatever system into whatever other system. I don't care. It's just the dimensionality of this phase space which remains.
Well, I mean, in a sense, yes. If you say this particular Q's and P's I call canonical, you basically define a new symplectic structure. That's true. Whether you can describe the same system like a Hamiltonian system, that I don't know. That's another question.
No, but look, this is a bit strange. Then we are not agreeing on something very, very basic and very, very simple. In the following sense, so I write to P and Q, right? Now, if I do whatever transformations of this P and Q, I will get, if you want, another Hamiltonian with another omega, right? That's true. But the point is, it's just a transformation of coordinates. It's not a new system. It's just same system written in different variables. And this is definitely true. Now, of course, I can map it into another system. This is different. It's not transformation of my coordinates. It's a map to another system.
Yes, it's a map to another system, of course.
No, but mapping to another system is not same dynamics, then I don't care. You see, mapping just making transformations of coordinates, it's okay. If I map it to another system, then the only thing what remains is the dimensionality of my phase space and its topology, nothing else. Because I can map it to arbitrary one.
May I? Following your example, you change coordinates. You have the omega is the same omega, but in coordinates looks different. And you have the Hamiltonian that in the new coordinates look different. Then you take this symplectic form and you compute the Roux theorem. So you have, well, no, exactly not like this, no. You take the symplectic form that has these new coordinates as transform coordinates. This is a different symplectic form of the transformed one. So
basically, you want to first do transformation, obtain some Hamiltonian, and then forget that this symplectic form was not canonical.
Change the symplectic form. We change the symplectic form.
Well, then it's not same system. It's a different system.
It gives you the same curves.
No, yes. Because they will not be a map in one-to-one. Because map is P and Q.
Yes. You make the map in P and Q, then you take another symplectic form, and most probably you also need to change another Hamiltonian because the original one will not work. But if you change another symplectic form and another Hamiltonian, voila, gives you the same system.
No, wait. But then there is no transfer. You see, there is no, how to say it. Okay, that becomes a bit tautological, I think. So the statement is very easy. So if you by hand change after that symplectic form, just by hand,
yes,
then you don't know how to transform original P and Q into new P and Q, no? Do you?
Yes. See, maybe there's not the same symplectic form that asymplectic form. You have a lot of different symplectic forms. You start with one. You take another symplectic form, you make the Roux theorem there, so you have different coordinates. So you have two sets of coordinates, you can transform between them. You can do that. But if you transform the symplectic form, you don't lead to the other symplectic form. No. You lead to a new symplectic. You have to use another symplectic form in this sense.
But then it's a substitution. Then you change. Basically, look, if I do transformation, let's say non-canonical, I just get same form which was before canonical, now in non-canonical form, but it's the same time. Right?
No, but we don't use that. We use another.
No, but then you change the system.
The point is, I change the if you think a system as a symplectic form and a Hamiltonian, yes, you're changing the system, but this is a geometric definition. But you can have two Hamiltonian systems, two pairs of omega and h that are different, that give you the same curves.
Okay. Now I got you. So basically, what you want to say is the following. Let's say in Pius-Uhlenbeck oscillator, that's probably a perfect example.
Yes.
Of course, if I do canonical transformation, I never change the sign of total Hamiltonian, but in reality, it's not needed because it's anyway two different guys. I could introduce two normal Hamiltonians for both of them and don't care about it. Is it correct? So physically substitute instead of basically that would say instead of Pius-Uhlenbeck, I use two normal oscillators and I
the point of Pius-Uhlenbeck is this more easy case where you don't need to change the symplectic form. And it's also our case, but your case, if it is by Hamiltonian that I don't know, it should be in this more weird case that you also have changed the symplectic form.
Aaron,
So
do you want to
basically,
intervene?
the statement would be, I need by hand. Let's say, okay, now I understand you better. So somehow the claim would be, I take this integral of motion. Now my new coordinates are not even related as proper transformations to my previous coordinates.
Bueno, but change of coordinates are not related to the symplectic structure, just a general change of coordinates, whatever.
Yeah, of course, you allow for most general change of coordinates. But now, see, it's not that you just change coordinates, but you also by hand change now the omega.
Yes.
The selective form.
Yes.
Just
this is
by
changing
hand.
what it means Q and P.
Yeah. But basically, by changing it by hand, it would imply that this is. You see, then I'm not even sure. It's not in that sense. It is mapping between different symplectic manifolds. Yeah.
As different symplectic manifolds. Yes.
Okay. Good. Now I
Yes.
understand much better what you mean. But then basically, if you require that look, I don't think it's actually possible that you cannot connect them.
As a change of variables in your manifold, yes. The
relation
between the symplectic structures, the theory about the Hamiltonian systems actually started because if you have more properties, they are compatible. Actually, the fact that you have a second symplectic structure gives you information about the first. Actually, they tell you how to construct infinite conserved quantities. So by Hamiltonians, start as a way to start your original system. And it's also how it is quarter debris is studied and these kind of things.
Right. But you see, it's in a sense, it's substituting a new system in reality. So basically, you find new systems such that P and Qs evolve in the same way.
Here, I know maybe the mathematician of the discussion, but anyway, I think that I have seen a lot of different mathematical descriptions of the same thing. So I will not think about the mathematical structure. I think it's more important to think about what's my physical system. And usually there is a lot of mathematical descriptions of the same thing.
Sure. But in reality, see, what I would be more worried about is the following. Suppose I have a source, some measuring device, and I measure, let's say, Q. And I'm not sure that if I do the transformation, I will measure same Q after that.
That's a very good question. You have said before, I have to think about that. When you think about observables in a more algebraic or geometric way, the observables are related to your symplectic form. So changing the symplectic form is also changing what you mean by observable, what are your observables, what is the way you understand measuring your system.
Sure.
So it's not easy to answer that. So because
but you see, that's in reality what I would care. Let's say I do the measurement von Neumann. I couple linearly these two guys. I know to what I am coupled to. After that, of course, you can do whatever transformations in this P, Q, doesn't matter. I couple to some combination of these guys. The most important thing is that if I do canonical transformation, what I will measure in my device, it's the same.
Maybe what will happen is that what's the mathematical expression of the observable may be very different in one system than the other.
Right. No, but you see, it's a question more of a coupling. Let's say I have a set of partial, differential equations. I couple to whatever. Now this whatever I can change. It's still some object to which I couple.
That's the point. you can have the same differential equations, and you can have a lot of Lagrangians and symplectic structure that gives you the same PDEs or the same differential equations. That is a big problem in my community. That's the problem of equivalent Lagrangians and equivalent symplectic structures. That there is a very different geometric things that give you the same differential equations.
Right. But what actually precludes you from having them all the same if you have same phase space, let's say dimensionality and topology?
The point is you have to find this, how to say it? I'm not saying that mapping each dynamical system to another dynamical system. I'm just saying that you have to find two symplectic structures that give you the same dynamics. And this actually is a very strong condition in these two symplectic structures. They are related somehow in a non-trivial way, but they are related. It's not that you can take anything and relate it. It's not like that. Because as you say, the dynamics can be topologically different. So you cannot relate any dynamic to any dynamic, of course.
Okay. So basically there is no, so you think that there is an abstraction.
Yes. And yeah, being by Hamiltonian is a very strong condition, of course.
Yeah, can I just say, just for the sake of putting an overall frame around the discussion. First of all, being by Hamiltonian is stronger than being integrable. So we are discussing a very selected family of systems. They just happen to appear a lot for those systems where we can analytically prove stability for at least a priori ghost system. So they happen naturally. They are a rarity in general, and they do happen with quite a lot of abundance in this particular topic. Then on the other hand, not everything does. There are stringent conditions, and in particular, this means that most of the systems are not by Hamiltonian. It's quite stringent to be by Hamiltonian, but if you are ghost stable, it's not out of place to see and ask whether you are within this range. In particular, because of the massive work of the Tomsk school, all of them are by construction by Hamiltonian. So there is a systematization of how to get stable ghosts, and they are by Hamiltonian. And
But are we by Hamiltonian? What we had with Aaron and Shinji and Cedric, are we by Hamiltonian?
Yes.
I think the answer is that no one. No.
I think
the answer is that
they
no one
are
knows.
by construction proudly by Hamiltonian.
Sorry. Yeah. We say that what the work of Hale and Bigman, we have not checked if you are by Hamiltonian or not. As far as we have checked, you are not by Hamiltonian. But it's hard to be exhaustive in this sense.
Okay, so basically you are not claiming...
Can I first summarize what I understood, and then I have a follow-up question. So I understood that a bi-Hamiltonian system is really a system where you have two sets of Hamiltonians and symplectic structures, which are, of course, related by some mapping because they live in the same phase-space dimensionality, and they generate the same equations of motion, which means they map on every solution, every phase-space point to each other consistently. That's different from just mapping two solution spaces onto each other. That's what I understood a bi-Hamiltonian system is. So now you also said that every bi-Hamiltonian system is integrable. Is that correct? But not necessarily every integrable system is bi-Hamiltonian. Okay, and for the Tomsk class of models, we understand, or you understand, that all these systems are bi-Hamiltonian, or by construction they're bi-Hamiltonian?
Well, they say it explicitly by construction.
Yeah.
Their entire methodology works on this. For instance, I really like their 2018 later paper. It's quite big, and they do catch up a bit in the... I think in our paper, in any case, we point out which one has a kind of summary for an introduction of their previous work, which I think helps a lot digest it, because I also think they grew wiser as they learned it. And I would say, disclaimer, I'm not the Hamiltonian lady, so probably you are better off learning from bi-algebraists in the mathematics department and from the Tom's colleagues who have made a serious contribution to this field and should be very comfortable with it. But with everything you said, yes, I agree. This is also my personal understanding after meeting them quite unexpectedly.
Okay, and then in distinction, we don't know at present if the models that Cedric, Shinji, Alex, and I constructed are of bi-Hamiltonian nature. They could be, because we haven't proven that they can't be. And what you're asking is whether one could achieve a proof of either these models or some other integrable model which is stable and has a ghost, that it cannot be bi-Hamiltonian, right? Okay,
So
and
I would say I just really liked this one comment of a Smilga in 2008 to some work by other colleagues on the Pais Uhlenbeck. And I found it very interesting, so that if I want to be extremely conservative, as I defend one should be only for science. So if I want to be very conservative, so that I want to call ghost to what really genuinely is a ghost and cannot do anything else in this life, then I must exclude the possibility that is only a ghost in one of its bi-Hamiltonian descriptions and not in all, should I be in such a scenario. And there are two ways to avoid this. Either you're not bi-Hamiltonian and then your conserved quantity can do whatever it wants. That's okay. It's a rarity to be a bi-Hamiltonian, generally speaking. So then if you're not bi-Hamiltonian, that's it. Now, if you have a conserved quantity that does the job and that is bounded from below, you have to do this check if you want to claim yourself ghost in the most stringent possible understanding of what it means to be a ghost. If your conserved quantity that does the job is not bounded from below, your Hamiltonian original was a supposed ghost, was not bounded from below, then I would say you're just fine and you don't even need to check. We, for completeness, did check and we were bi-Hamiltonian ourselves. And that's why we were just curious, because so many examples of the ones that are coming in a new batch, they are all happening to be bi-Hamiltonian, that the question arises, to what extent is this?
I would say we have I would disagree. We have two batches of models, one for which we know that they are bi-Hamiltonian and one for which we just don't know whether they are bi-Hamiltonian.
Correct.
And for the ones, so to sort of move beyond language, I think, so first of all, thanks. I think this settles a little bit of my understanding. And then are you aware of classes of integrable systems for which it's known that they are not bi-Hamiltonian?
How to even check it? I mean, easily.
Because you said it's rare. So if you said it's rare, it suggests that somehow there's an understanding that there are classes for which one can show that they're not bi-Hamiltonian, right?
Yeah. So sometimes there are like, necessary conditions to be bi-Hamiltonian. So if you break one of the necessary conditions, then you are not. You are suspicious if you are integrable a priori, and you know you are integrable, because you might be integrable and not know about it, because it's an open, difficult question to know all your conserved quantities for a fixed given system. And so it's not so simple, and I don't think there is something called the ultimate list of do A, B, C, D, and boom, there you go. You are bi-Hamiltonian. There are examples of even integrable, of course. If you're not integrable, no question.
I don't want to find all bi-Hamiltonian systems. I want to have a check to exclude that a system is bi-Hamiltonian.
Yeah.
So,
is it possible?
So that's problematic, because say, for example, what can happen and what we did, so there are different levels of trigger in which you can check. No? So for our example that we cooked up as we could, the easiest check was already telling us that we were bi-Hamiltonian. So then, great, we are bi-Hamiltonian, that's it. And a bunch of our, because our system is again a family of systems depending on a function, a bunch of functions, if you bound them from below, then that's it, you're done for. We have stable systems, but they are not ghost. You have to unbound them from below. Okay. Now, you can be, so these are, let's say, a first batch of necessary conditions that you must satisfy. And if you satisfy certain conditions, then the check for bi-Hamiltonianity is kind of simple. If you don't check those necessary conditions, then you start entering a more complicated realm of cross-checking whether you are bi-Hamiltonian, yes or no. Your work with Alex et al. Would enter that realm. So we passed the first check. We couldn't tell that you are Hamiltonian, let's say, in the face in a simple manner. It requires further work. In the end of the day, for me, it's a curiosity, but if you wish, it remains an open question. Now, is there an ultimate exhaustive list of checks and sort of systematization to check, no matter what condition you are in, that you are bi-Hamiltonian, yes or no? I am not aware of it. Are you, Jordi?
No, I'm not an expert in this thing in particular, but all the things I do is that they give you 2 symplectic extractions and then you check things. But there's a lot of symplectic extractions to check. If you do it by hand, you have a PD on your Hamiltonian, if you start a PD, so you can do it by hand if you want, but it's convoluted algebraically. And just to add on your comment, Vero, that even if your system is like Hamiltonian, you can be ghost if all your Hamiltonians are unbounded from below.
Sure.
Yeah.
By the way, but then I'm very much puzzled because
Sorry, Alex. I mean, let me just interrupt you to stop the recording.